Micromobility is transforming urban transportation. E-bikes and scooters are efficient, affordable, and sustainable, but there is a major downside. Limited battery range and long charging times are holding micromobility back. E-bikes typically run out of power after 25 to 45 miles, requiring hours to recharge. On the other hand, gasoline-powered scooters provide longer range and instant refueling. They come with noise, emissions, and higher operating costs. For gig workers and commuters, running out of power mid-shift or during a trip means lost time and lost income. ICE proposes a hybrid transmission solution, combining an electric motor and combustion engine to balance out the weaknesses of each individual system. This allows us to extend the range of the transmission system while designing around a lightweight and low-profile integration with the vehicle. Our design is unique in the automotive industry, as transmission systems exist for larger vehicles such as cars, heavy-duty construction vehicles, and commercial buses. There are no existing viable solutions, however, for smaller, micromobility-oriented vehicles such as bicycles and scooters. The selected engine is the Honda GX50, used commonly in agricultural settings, lawn equipment such as trimmers, water pumps, and small-scale vehicles such as go-karts. It has optimal power output while maintaining a smaller frame, which is a perfect combination when integrating with micromobility devices. The selected motor is FlipSky's 770 motor, rated for 170 kV. This motor is used extensively in existing e-scooters and e-skateboards. These two components were selected using expected rider profiles while in use of the transmission. The two figures highlight the expected torque and acceleration curves for various models. A particular focus of our design is the cone clutch that connects the engine to the driving shaft of the transmission. It is actuated by a servo to seamlessly transition from motor to engine power depending on the riding conditions. When activated, the clutch creates a seal allowing for power transfer from the engine to the overall system. Breaking the seal by moving part of the clutch back disconnects the engine. This clutch design was chosen for its simple design and ability to transmit higher torque than plate clutches of similar sizes. This is due to the frictional force being produced by the conical design. The overall design architecture consists of the engine connected to a conical clutch and the pulley and belt connection to the main gear train to deliver the reduced power output. A belt drive was chosen for ease of maintenance and greater flexibility to allow for easy implementation with our shaft designs. An example of the transmission usage is when wanting to cruise at lower speeds, the motor would be used and the clutch would be disengaged to not connect the engine to the driving shaft. When the engine is in use and when operating at high speeds, motor regeneration is also possible as the excess backward motion of the undriven motor can charge the battery. Our solution for the current micromobility problem is to reduce range anxiety and downtime commonly reported by users of e-bikes and scooters, while preserving the same power output of traditional electrical or mechanical systems. We aim to present an alternative to traditional power systems by combining and maximizing the power output of mechanical and electrical systems to empower micromobility users such as delivery drivers, gig workers, and daily commuters. Our innovative design introduces a conical clutch that allows for seamless transition from motor and engine power. With compact housing, this transmission system can be readily integrated into micromobility devices and vehicles. With this design being the first on the market, this prototype can be used as a framework for further development to more efficient and powerful hybrid transmission systems for micromobility.